MOSFET amplifiers are not terribly difficult. You almost know everything about them already because we've done the DC part, and the DC part is part of it. But there are certain things that we do to analyze the AC circuits that's a little different from the DC. So I think I said long ago that amplifier analysis is basically, they're analyzed using superposition, which when you learn about superposition when you are in circuits, it seems stupid because it makes more work. But in reality, when you're doing a DC analysis and then you do an AC analysis, that's superposition. So when we look at the AC circuit, we will know everything about the DC circuit, but the DC circuit will be turned off for the analysis part. So anything that's connected to the DC circuit looks like ground to AC because that's how we're doing the analysis. And it will make more sense as we go through and do it. So amplifiers, MOSFET amplifiers, and this all applies to pretty much the next type of transistor we do too. They're designed so the bias point is somewhere so that if the signal moves up and down a little bit, it won't go into the triode region or into the cutoff region. So it's somewhere in saturation, and it is already biased, and hopefully we already know the DC parameters as such. So we keep the AC signal small. So we don't put in 10 volts peak to peak in an amplifier. We put in like 1 volt peak to peak, or sometimes 1/10 of a volt peak to peak, because it's going to increase and the output is going to be limited by whatever voltage source, DC source you're using to power the amp. So there's a certain limitation. And as I said, since there are AC and DC sources, we use superposition to analyze them. And last week we talked about the DC part. And generally what you want from the DC part is a couple of DC parameters that we use to find one particular value. And then once we find that value, we translate it to the AC circuit, and we forget about the DC circuit completely. So we find the DC bias point, we ignore the AC, and then we use a model for the transistor that takes into account what we found from the DC circuit without including the DC circuit. So we include we obviously include the resistors that are part of the DC circuit, unless for some reason they're shorted, but we don't really cover how they get shorted in here. If you put a capacitor in parallel with a resistor in a DC circuit, when you turn on AC, it shorts it to ground and it becomes not part of the circuit. But we don't tend to do that so much in here. So we're going to look at what models we do first, because there's actually 3 different ones we use depending on the type of configuration we have. So the first model is basically similar to the large signal model we did a while back when we were doing characteristics, which was like 2 weeks ago. It's a little bit different, and this is what we call the pi model, and it is because in general it goes up and out kind of like the pi symbol, but we don't use the pi symbol, but it's called the pi model. And this is the pi model when lambda equals 0. So this is the simplest model you can get. The output impedance is infinite because it's just looking into that current source, and the current source doesn't have any resistance to it. And then the input impedance is, in this particular model, an open circuit. Some models will make it so it's not an open circuit, depending on what configuration we use. But in the model itself, we assume that the input impedance is infinite, even though at some frequencies, which again we don't really cover in here, there is a capacitance across that, and that actually does appear eventually. The only thing that you don't know about yet is the transconductance parameter GM, which we'll cover in a minute. But as you can see, that transconductance parameter is what determines what comes out of the amplifier. So that is an important parameter, and it's actually one we get from the DC circuit. So that's the first model that we can use. The second one is almost the same. It's just used when lambda is not 0. Remember, when lambda is not 0, we have the channel length modulation being equal to something. and that gives us an output resistance. And that output resistance runs from the drain to the source, and we can figure that out either if we know the A or if we know lambda, and then we need to know the DC current. So that's one thing that ID is used for in the model, is to figure out what RO is. So those are the two most common models. They actually oftentimes, when used, create weird circuits to analyze. So there's a second model that is also used. Depending on what kind of circuit you're using, it may actually make the analysis easier. And of course, once we go through all the analyses with all the models, you probably won't have to much use the models, but you may. So it's good to know how to use them. So that's the second model. And then sometimes we have to make some changes. So there's a second or a third, I guess, type of model we can use. So if we take the standard pi model without RO in it, and we know that the current GM-VGS goes around that corner. So it comes out of the drain and goes down. So if we put a second current source there, it doesn't matter because they're going to be the same. And since we know that there is no current going into the gate, we can actually run that gate connection all the way over, because it's not going to change the circuit because there's no current coming in. So we still have GM-VGS and GM-VGS going across and down without changing. Once we do that, we can actually replace the lower current source with something equivalent that is going to do the same thing. So right now, we have a current source that's GM-VGS, and we have a voltage across it of VGS. So if we want the same current, if we take VGS and multiply it by 1 over GM, we get that current. So if we just replace that with a resistor of 1 over GM, if you were to calculate the current in that resistor, it would be GM-VGS. So it does the same thing. The last thing that happens with this model, it's usually rotated. So it usually looks like that. So all I did was take the one arm and flip it up. That is known as the T model. And especially if there's a resistor from the source to ground, this one is much easier to use than the previous one. So in circuits where there's a resistor from the source to ground, that makes the analysis easier. So the three models are not difficult to use. The one thing that you don't know is where this GM value comes from. And that is known as the transconductance. The transconductance is basically determined by the DC circuit. So we're going to look at the DC circuit for a minute and kind of go through and figure out how to get that value. We have the Q point set by the DC circuit, and then the AC signal moves the Q point along the load line. And this is a really, really simple, basic DC circuit. There is an AC source in here. So basically, this is designed to show you, in the simplest way, that the input is a combination of DC and AC sources. The DC is VGS and VDD. Those are the two DC values. That DC value of VGS could be made using a voltage divider or something else, but right now we're just modeling it as a voltage source. And then the time-dependent AC source is the signal you're actually putting in to amplify. So what you get out at plus to minus VDS, you notice it has a little v and then a capital DS. That is what the textbook uses to signify a signal that is mixed, that has DC and AC components. The standard way of representing signals is we use all capital letters for DC and all lowercase for AC, and then we use a combination for signals that are AC and DC. So little v, capital G, capital S is a combination of the DC signal, VGS, and the time-dependent signal, little v, little g, little s. So that's kind of how it's shown. So now we have to just do math, basically. When we look at any particular time in the process of running the circuit, the gate to source voltage is always going to be a combination of the DC and the AC. And we can actually put that into the original drain current equation that we had, except now the drain current equation contains AC and DC parts. So you notice it's a little I with a capital D, which means it's a combination of DC current and AC current. And we still use the same Kn prime over 2 W over L, but now we're multiplying it by VGS of its two forms. So we have the DC and the AC put together, and then we take off the DC threshold voltage. And what I'm going to do is just take all those terms in the square and kind of separate them out into DC and AC by just multiplying everything together. So what we get is kind of a long series of things. We have a DC part. That's the part where we use to find the DC current. And if the AC is turned off, everything with anything AC multiplied by it goes away. So if we were just looking at a DC circuit, the 2 VGS minus V threshold and little VGS would go away because little VGS would be equal to 0, and then the little VGS squared would go away. So if we were looking at DC only, we would see the original equation we've been using so far. Then in the middle, there's what we call an AC linear term. The DC value is multiplied by the AC value multiplied by 2. And then the last thing we have is something known as the AC nonlinear term. It's not going to be as complicated as it looks. Basically, the DC term determines the drain current in DC. So in AC analysis, we knock that out. The nonlinear AC term is also really, really small and can be knocked out. So when we want to just find the AC drain current by itself, we just use the part of the circuit analysis that includes the AC term that's not the square. So we end up with this, which is not terrible. This is actually, and you notice that the Kn prime has no 2 over it because in the previous slide there was a 2 in front of the VGS minus V threshold VGS. So that's where that 2 goes. So don't get confused. The 2 goes away when you're doing the AC analysis. And that is the equation that gives you the AC current. And the cool thing is that the AC drain current is pretty much a linear function of little VGS. So that makes it not so terrible. So where do we get little GM, the transconductance? The transconductance is defined as the AC drain current divided by the AC gate to source voltage. So it's basically defined this way. Little ID over little v, little g, little s. Since it's a conductance, it's I over V. If it was a resistance, it would be V over I. So that's just the inverse of the value of, well, whatever. Sorry, I lost my train of thought. Anyway, in order to find that, if we take ID, which was Kn prime W over L, VGS minus V threshold times VGS, and we divide that by VGS, we just get the original equation without the VGS part. The VGS just cancels, which means we can calculate GM that way if we know VGS and V threshold, and we could also, if we knew the overdrive voltage, calculate it that way. So there's a couple of different ways we could calculate it. Most of the time we don't use the overdrive voltage, but you could. That is, and there's actually 2 other ways to calculate it, which I'll cover it later. But this is what the DC values in the circuit are used for, is finding the transconductance, because that goes straight into the AC model. So the DC drain current, whatever that might be, is actually what has kind of an effect on this value, or VGS. So now that we're talking about AC circuits and we know what transconductance is for a minute, the thing that we really usually want to know about amplifiers in general, remember way back, I don't know how long ago it was, but way back we were covering amplifiers in general, and we talked about input resistance and output resistance and how the input resistance and output resistance could be creating voltage division with signal resistance input and load resistance output or whatever. We did that a while back. But this is where the input resistance and output resistance actually is important, because we actually do need to know this. And we need to know what the voltage gain is. So the voltage gain is just defined to be the ratio of the output voltage to the input voltage, and this would be the AC output divided by the AC input. So in a MOSFET amplifier, Vn is usually equal to VGS. Not always, but for this particular day, today, it is. Not always will that happen, but for this particular illustration, because of the one we showed earlier, that is what's true. And V out is actually equal to VDS. Like I said, when we talk about different amplifier classifications, some of them this will not be true. So do not take this as being always true, because it's not always true. It's true today for the particular amplifier I showed and that I will analyze, but not always. Don't look too confused. I know. Don't get confused. It's okay.
Is it going to be different on Wednesday?
Yes, but it's amplifier specific. So for the amplifier that I showed, which is a very, very general amplifier, this is true. And it will help us get to an end point, yes.
Will it be different on Friday?
Maybe? It's okay. The cool thing is everything will digest down into something really simple. Because you guys are engineering students, I have to show you how we get to the end, mathematically. But you will know what the end result is, and it will be not difficult. You can put it all in a table, if that helps. So, if we look at the drain to source voltage, which is where the output is going to be, it has a combination of DC and AC voltages, just like the drain current was. So VDS, which is little v, capital D, capital S, means it's a combination, has VDD, which was the DC source, minus ID, which is a combination of AC and DC, times whatever the drain resistance happens to be. So we can split that drain current up into an AC and a DC part. And then we can collect the DC and AC terms. So now we have VDD minus ID RD, all capital letters, which is the DC value of VDS minus the AC current times RD. So that is kind of what gives us the value at the output. And if you think about it, it's just saying that you have a DC value VDS, and then there's going to be actually a fluctuating value, because ID is actually, because it's an AC value, is going to go up and down slightly. So it's just going to go up and down a little bit, the voltage right at the output. And it actually go up and down quite a bit, because it's the output. But once we've done that, we can figure out VDS, because it's a combination of the two. And we have VDS minus ID RD. So basically I took two different equations that determine what VDS is, because I really want to know what little v, little d, little s is, which is minus ID RD. And because I know that GM is supposed to be that current GM VDS from the particular output of the model, that is supposed to be the output voltage times the transconductance. That's what ID is equal to. We can get the voltage gain from using these two values, because we need to just know what VDS and VGS are. So that is the value. The gain, and this is, remember there were 3 types of voltage gains from way back when. One was AVO, which was just the amplifier. Yeah, I know, sure. You remember, don't remember. I'm going to explain it again next time also. I will tell you the difference. AV is supposed to be the voltage gain without a load resistor, basically. Actually, AVO is usually the voltage gain without a load resistor, but again, it won't matter because you'll just need to find the voltage gain for the whole circuit, and that, that won't make any difference. So it'll be okay. So that is the voltage gain. The voltage gain of an amplifier, a MOSFET amplifier, is just the transconductance times the drain resistance. And it's negative because it's inverting. So if you're asked for, say, the peak, if you know the peak voltage at the input, you're asked for the peak voltage at the output, you don't have to worry about the negative. The negative is just saying the output's inverted. So you don't have to say it's negative something. You just are saying a peak value, so it's just a peak value. If you do say it's negative something, I won't fuss too much. But so this is how it works with the actual model. That was our original circuit. So you notice that RD is outside of the MOSFET, and the only model we were looking at initially was just the MOSFET in and of itself. All right, so if we are going to put that circuit into the model, all we have to do is add RD. That's the only resistor that we're really worrying about. And you notice it's kind of outside, and that has VDS across it. And the gain is minus GM RD. So if we have lambda equals 0 and no RO, we just put RD sort of out from the drain to ground because the source is grounded, and we're done. And then we can analyze the circuit as needed. If we have a model where lambda is not 0, we add in RO. And RD is in parallel with RO as long as the source is connected to ground. If it's not connected to ground, that's when we use the T model and we have a completely different analysis. So in this circuit, we can get the gain by just taking minus GM RD in parallel with RO, and that will basically reduce the, well, it probably won't reduce the gain much because RO is usually much bigger than RD. So the two in parallel is going to be less. RD is going to go down, but not significantly so. But it will reduce the gain a little bit. So I said earlier that there were 3 ways to find transconductance, and this is actually very useful. And I'm not going to go through mathematically and tell you, how we get to all of them. You can figure it out. It's really pretty easy. It depends on what DC values and parameters you know. So if you happen to know Kn prime W over L and VGS, you can find it that way, and you have to have the threshold voltage. So that was the original one that we used. But we can also factor in the ID equation, and you can, if you happen to know ID instead, you can calculate it this way, and you will get the same value. And if you don't know Kn prime W over L at all, but you happen to know VGS and ID, you can find GM that way. So depending on what you've found in the circuit, what you've been given, you can do 3 different ways to find the transconductance. And always use the one that you have the parameters for. Don't go try to figure out parameters you don't have. You're going to need 2. You're either going to have Kn prime W over L in either VGS or ID, but if you happen to just have VGS and ID, just go ahead and calculate it that way. Don't try to figure out the other parameter. And I think that's in the homework. You get to practice that. So we will do, that is a very, very, very long example, but it's probably a good example. A long example. We have an actual MOSFET circuit, and this is not, it's not as bad as it looks. Yeah, and that's what always happens. The minute you put the AC and the DC together, students freak out. I will tell you that on a test, I don't put DC and AC together like that. What I do sometimes is I say, okay, this DC circuit has been biased this way, now find the AC parts. But I generally don't make you go from beginning to end because it's too easy to get the wrong number somewhere in the middle and then totally mess it up. So this is an actual MOSFET type amplifier. It's not one of the ones we're going to study on Wednesday, but it is a sort of a typical one. And you're given the threshold voltage, Kn prime W over L, and VA. So we know kind of what model we need to use from that value. We know that the source is connected to ground, so we can use one of the pi models, and lambda does not equal 0, so we have to use that one with RO. The capacitors in the circuit are assumed to be short for AC and open for DC. So they are of such a value that they don't affect the circuit as far as impedance goes. Since we don't cover frequency effects in this class, we don't have to worry about what might happen if these capacitors actually had an impedance. So the assumption is, during the DC analysis, anything on the outside that's connected with a capacitor just goes away. And for the AC analysis, the capacitors just become wires, and the DC circuit is, the DC source is shorted to ground. So we want to find AV and Rn, which is always a good parameter to look at. So the first thing that has to be done is we have to analyze the DC circuit, which basically means getting rid of the AC part. So when we do that, we basically just take away anything that's AC, and we're just going to look at the DC part of the circuit. Also, we remember that there is no current going into the gate, no DC, no AC. So there is no current flowing into the gate in this circuit, which means that the current through RD is the same as the current going down through the MOSFET, and it doesn't change. We can analyze, remember that this is the type of feedback circuit in which VGS and VDS are equal because the drain and the gate are connected together. There's no current going through RG, there's no voltage drop. So we know that VGS equals VDS equals VDD minus RD, which is just regular circuit analysis, and we know the transistor's in saturation because VDS equals VGS, and that's greater than V overdrive. Again, if I tell you to analyze a circuit, I will generally tell you that it's in saturation or not, so you don't have to struggle with wondering if it might be. So if it's in saturation, it's going to be working as an amplifier. So we take the above equation and we substitute it into the ID equation. And when we do that, we take VGS and we substitute VDD minus RDID into that equation. And it's already starting to look, fun. Once we do that, we can actually put numbers in there. We have 0.25 milli divided by 2 for Kn prime W over L. So we actually divide that by 2 and put that number there. We have VDD was 15, RD was 10K times ID, and then we subtract 1.5, which was the threshold voltage, and put all that together, and then just multiply it all out. And I'm reasonably certain, like all my numbers today are correct. That's been a problem lately because I keep getting distracted by other things and then I forget. And the interesting thing is I was actually using another example for which the numbers were not correct. So I had to check 3 times because I kept getting different numbers than what I was looking at. and I'm convinced mine are right, and Dr. Thane's are not. So there you go. Anyway, we get a quadratic equation for which we can solve just like we did before, and we get two numbers for ID. And remember, pretty much every single time it's going to be the lower number that is the actual ID value. If we were to take 1.72 milliamps and multiply by RD, which is 10K, we would get a number bigger than VDD, so that doesn't work. So the 1.6 milliamps is the actual value of ID. Once we find that value, we're going to substitute the value of ID into the equation to find VGS, and we get 4.4 volts for that. So this is good. Now we know ID and we know VGS. We also knew Kn prime W over L as well, but we're just going to use ID and VGS to find the value of GM. So when we do that, we substitute in numbers and we get 7.3. You can do millisiemens, you can do milliamps per volt. It doesn't really matter. Just make sure you have some kind of unit. I think I mostly use amps per volt, but this particular time I didn't. The other thing we need to find is R out, since there was actually a value of VA given, and we just take the value of VA and divide by ID, and we get 4.7 kiloohms. So now that we've done all that, that's all we need from the DC circuit. That's it. We need GM and we need R out. If there is no R out or VA or lambda given, then we don't worry about R out. But we do need to find GM. Once we have found that value, now we go and use the model to actually add values in. So we start with the model, and I put a little thing of the circuit so that we could actually relate it back to the real circuit. And we're going to look at each point individually just to see how to put these together. I am not going to do this more than one time. So most of the time I'll just say, hey, this is how the circuit works. But in looking at the source is connected to ground. So we just put a little ground symbol at the source, and we've taken care of that. I don't remember what order these go in. So for RG is connected between the gate and the drain. So on the model, we have to put it between the gate and the drain. So we put it in the exact place that it would occur. The next one we look at is RD. RD is connected from the drain to VDD, but VDD is ground because we've turned it off. So it's actually connected in parallel with RO because it's going from the drain to ground. So that's how we put it in there. And the load resistor is also connected from the drain to ground. So that goes in parallel with RD. So we've got actually 3 resistors in parallel, which is going to make the whole thing a little easier. And the last thing we have is the input voltage. The input voltage is connected from the gate to ground, so we just put it at the input. And that is the complete AC circuit with GM that we know and RO, which we know. So that's basically what we do. I'm not going to put numbers in yet, though, because this is still a more general thing that we can do. First of all, the 3 resistors at the output are all in parallel. So to make this a little easier, we can combine them all into one resistor value that has RO in parallel with RD in parallel with RL. And I just call that RL prime because then we aren't going to have to write out all those parallel values. And the gain is described or defined as V out over V in. And the input resistance is defined as Vn over In. So all we have to do is find those values and plug them in and we're done, which sometimes is easier said than done. So we have everything kind of marked on here. First of all, In is the current going into the gate. And you'll notice that it's not 0. It's not 0 because of that gate resistor. So it can not be 0. It cannot, well, not, it's not infinite. Yeah, that's right. The current is 0. The input is not infinity. So the input current is not 0 in this particular configuration. And the current from the transconductance, if we want to know the load current, RL prime, we basically take the input current and subtract off GM-VGS, which is the current going in the dependent source. That's just using current division or whatever. So that's why that's written in there, because I'm going to need it in a minute. VGS is equal to VN in this circuit. Like I said, in all amplifier circuits, that won't be the case, but today, it's the case. And then we have V out, and V out is equal to RL prime times IN minus GM VGS. That would give us whatever V out is. And V out is also equal to VDS because it's between the drain and the source. So there's a couple of ways to deal with that. So first of all, we're going to find AV. Oh, okay, I didn't fix that there, did I? Okay, well, I'll fix it here. I did notice something this morning, and then I didn't notice in the previous slide. Not that it matters. It doesn't change anything. So V out, like I said, is IN minus GM VGS. That's the current through RL prime times RL prime. Which means I can split things out a little bit because Vn is actually part of that equation. VGS and Vn are the same, so I can just substitute that in. In is Vn minus V out over Rg, since V out is where the drain is, and that's the voltage at the other side of Rg. So we've got an equation that actually describes that. Now it gets very, very mathy for a minute. We can actually take IN and substitute it into the beginning equation. And the cool thing is, once I'm done, you'll never actually have to do this yourself. You just need to know where it comes from. And then you can just memorize what the formulas are or whatever. Although you do need to know where they come from. So we take Vn minus V out over Rg. And then we subtract VGM Vn, multiply by RL prime. And then we're going to take 1 over Rg out, which means we end up with this RL prime over Rg and times this Vn minus V out. And eventually we're going to get V out and Vn on separate sides. That's what we need to do, basically. So V out is RL prime over Rg Vn minus RL prime over Rg V out minus RL prime GM Vn. And then we can actually finally split out V out and Vn. So we're getting really close. Because really all we have to do is just take V out over Vn, which means to take those two large fractions and put one over each other. So we can factor out this 1 minus 1 over GM Rg. And then since we have V out over Vn, we get this really insane thing that kind of looks like initially what we got. Remember, we got minus GM RD as the gain of the simpler amp, and now we're getting GM RL prime times this kind of big ratio. Well, the cool thing is that this part is about 1 because RG is really large. And that's one reason we make RG really large. We had this conversation in class about why do we have RG? Why is RG made really big? This is one reason why, because it makes its effect not affect the circuit. If RG was small, then the gain would change dramatically. So that's why it's usually in the mega ohm range, because then that whole fraction is gone, and then AV is minus GM RL prime, which looks a lot like the other gains that we got. We got minus GM RD, we got minus GM RD in parallel with RO, and now with adding a load resistor, we get minus GM RO in parallel with RD in parallel with RL. So all we're doing is putting that last resistor in parallel with the rest of the stuff we figured out. then we can calculate AV. So that's why I didn't put in numbers until now, because most of the stuff goes away. We know all the numbers. We know GM is 0.0073. We know we can take those three resistors in parallel and we get minus 3.3. And what this means is that the output will be 3.3 times bigger and inverted. So again, if the peak input is one value and you're asked for the peak output, the negative sign isn't going to make a difference. In fact, the negative sign would give you the peak negative, but you don't necessarily have to include the negative sign for that. That's just telling you that it's inverted. Now, we went through all that trouble to determine that if we had just added RL in parallel with the other two values, we could have been done, but I had to show you why you could actually do that, and now you know. We have to find Rn, because Rn is a very important parameter for amplifiers. If you've got a signal coming in, the signal is going to have a resistance, and that signal resistance is going to create a voltage divider with Rn, so you're going to lose some of your voltage coming in if Rn is really small. So we want Vn over In, and we already know what In is. It's Rg Vn minus V out. And then we can actually factor out a Vn, or put in a Vn minus GM RL prime Vn, and then just take the Vn out. And we get Rg over 1 plus GM RL prime. And what that ends up doing is reducing the amount of input resistance from Rg. So it's going to be smaller than Rg, but not appreciably smaller, as long as the gain is not too big.